I want to bring up Professor Tim Chupp, who's going to talk to you about the physics of basketball. Let's give him a round of applause.
Okay, so the physics of Space Jam, the physics of basketball. So here we go. Some things happen in real life and some things don't. Which one is that? Okay, so as I said at the beginning, we're going to talk about hang time to start with, a little bit about cartoon physics, which seems to be a very important theme for this series anyway, and then shooting a basketball. So let's just start by having a look again at a really beautiful play. A lot of times you see them in slow motion, but sometimes they're in real motion. So I guess what we saw here is, try this again, is Michael. Do it, Michael. There we go. I mean, really soaring, right? And the question that I have for you, I like to start with questions, is let's take a look at the possible track or flight of Michael. And I have 3 possibilities here, and I just want to see what you think it could be, all right? Because, he takes off, he's hanging there in the sky, and then, of course, he does eventually come down. And that's moving as well. Right, so this is the height off the ground, and this is his position from where he took off to where he lands. You sort of understand what that graph means, right? So that's one of the possibilities. Think about that. Here's another possibility, somewhat more symmetric. And here's yet a third possibility, where he takes off here, and again, he's just hanging there. That's hang time. And then coming right down, all right? Which one, ladies and gentlemen, boys and girls, which one do you think it is? How many A's? Oh, a few A's, all right. How many B's? All right. And how many C's? All right, we like that one. Okay, well, it's probably closest to B, of course. You know that. At any rate, but actually, any of these shapes might work depending on what part of Michael you're watching, or what part of the person soaring and dunking that you watch. So this would be the right thing to answer on an exam, or if you're taking one of those entrance exams for postgraduate school, etc. That might be right, but actually, as I said, it depends on what part of the player you're watching. So what part do you watch? All right. Let's take a look at this. Amazing dunk. You can see it in slow motion as well. Julia serving here. All right, what are you watching there? Probably the ball, right? So the ball is doing some amazing things as Dr. J does his thing there. Okay, so it could be the ball. Maybe it's the hips, all right? I think I know how to show this again, so let's just take a look here. You know, you see some part of him, and you almost don't watch the ball, I think, at least I don't. But it does end up through the basket, so that's a really physical play. So it could be sort of the hips of the player, or the tongue, right, Michael's tongue. I think that helped him a lot, and to be a superstar. But actually, you might watch the center of mass, okay? But what is that? What is the center of mass? Well, I brought actually one visual aid, one thing here. Can you see this? All right. I hope they leave the lights on for a while. I asked them to turn them off because this is a smaller ball and a large ball with a rod here. So this is a model of a person, for example, here. And the point is that there is a place somewhere along this line where I could maybe hang it and it pretty much balances. And that defines the center of mass. So what I can do is, now we can take the lights down a little bit more, is I can even make my screen black. Okay. Is follow the center of mass on the flight of this, because I have a light at the center of mass. So let's just start by doing that. And I'm going to give it a throw. And actually, about how high do you think someone like Michael Jordan or one of these great basketball players jumps off the ground? You know? Right. Well, that's right. You look it up, and it's something on the order of 40 inches or a meter. At any rate, I'm going to try to throw this with an extra height of about a meter from where it starts, which is a little bit above my own center of gravity. And just keep an eye on this light, which is the center of gravity itself. Uh-oh. Can't leave the stage. All right. Good. So that was maybe somewhat like the textbook arc that you saw there? You tell me, because I can't see it from where I'm throwing it. Yeah? All right. But even though that's traveling in that way, another part of this, which is at the end of this device, can do something really quite different, I hope. It looked like that to you. In fact, there's even maybe a more spectacular thing that you can do, spinning this around. And one more time, while I spin it around, I'm going to show you the light at the center of the mass. Okay. So I hope what you saw, you can't see me now. Now I can have the lights back up. I hope what you saw is that with the light at the center of mass, it followed an arc just like the textbook arc, in spite of how complicated the motion at the end of this was. All right? So there's two lessons here. One of them is that the center of mass has a very predictable motion. It's governed mostly by gravity. And also where the center of mass is. Okay, the center of mass is closer to the big thing and further away from the small thing. Okay, and there's a kind of a nice way that we could calculate that. But what I'm going to do instead is show you a picture of our athlete, Michael, here, and kind of draw a couple of lines across some major diagonals, and where they meet, somewhere around the belly button, is the center of mass. Of course, that's where it all starts. Okay, so that center of mass will follow a fairly predictable trajectory, no matter what the rest of Michael does. So here it is. All right, so we're following the center of mass time after, okay, sort of equal time intervals here, and that is the path, the textbook path that you saw. So the center of mass will follow that path, even if the ball, the legs, and other things, the tongue, does something different. Okay, so the center of mass follows a simple path. Here's the math, okay? Did they tell you there'd be a quiz afterwards? All right, so the horizontal velocity, okay, the speed in the horizontal direction is effectively constant. So that doesn't change, and then this is maybe the simplest formula that I could write down in physics, that the distance increases with time, and we call this the proportionality, and this is the velocity. So the distance is proportional to the time, proportionality is the velocity. Okay, so that doesn't change. Horizontal velocity doesn't change. But in the vertical direction, Michael goes up until his vertical upward motion stops, and then he goes down and to the ground. And this is slightly more complicated, but I can just tell you that the time that he is in the air is approximately 1/5 or 2/10 of the vertical velocity if you write it in meters per second and the times in seconds. And how high he goes is about 1/20th of the square of the vertical velocity, the velocity he takes off with vertically. And that's in meters, and the velocity is in meters per second. Now, effectively means that you all know that there's the possibility of some kind of drag or air resistance as things move through the air, but it's really a small effect here. So there's Michael, again, in his center of mass, and if he doesn't have very much horizontal velocity, but leaves with a certain vertical velocity, there is his path. And that would be the same vertical velocity, but more horizontal velocity, same vertical velocity, even more horizontal velocity, and even more horizontal velocity, the same vertical velocity. And one thing about these possibilities, every one of these happens in a basketball game, it's taking off from the foul line and dunking it, or dunking it from just under the basket, like the monsters did a lot of the time. Every one of these takes the same length of time, because all that he does is go up and down. And that is the physics, part of the physics of hang time. These all take the same time, but you still have the illusion, or it seems at any rate, if not an illusion, it seems that he's spending quite a long time in the air. And that is in fact true, so it's not an illusion. In fact, about 70% of the time, just count the dots, okay? 70% of the time is in the upper half of this. So taking off is quicker. Gliding through the upper part of the trajectory takes half the time, and then at the very end. This takes 70% of the time, and at the very end, it's quicker again. Okay? So it's actually not just that there's certain parts of the body that are moving in complicated ways and give the impression of longer hang time, but there really is more time spent up high. And that is the physics of hang time. Here's some statistics about Michael. He's one of the greatest jumpers, apparently. There are many different ways people measure this, but he basically has a 40-inch or 1 meter vertical jump. The hang time, the time in the air is only about 9/10 of a second. And so another reason it seems longer is, of course, slow motion. If that is the case and he's traveling approximately from the foul line about 15 feet, then the vertical velocity is 4.5 meters per second. The horizontal velocity is 5 meters per second. The angle of takeoff is just under 45 degrees. And really astonishingly, the force that Michael produces in his legs as he is doing this is on the order of 4 Gs, 4 times the force of gravity normally. So that's the path he takes. Okay, cartoon physics. What we learned in the introductory little clip from the Sloan Foundation was that cartoon physics is not real, but it's almost real. And what's real about this? Well, eventually, he falls down, right? Maybe the physiology of the coyote is a little bit unusual, but I want to emphasize a couple things. One is that he falls, I timed this, it's 5.2 seconds, which means he fell about 330 feet or 100 meters. But watch this. This is just what happens to the coyote as he falls. Bizarre. That's not real at all. Okay, that's the strangest thing. So I do think it's realistic that at least he falls down in this case. But there's something else that I find very interesting about this, and so I'll show you again, is sort of the accordion nature of the animal. All right? The bottom part falls, and then the top part. That's very unusual that some part would fall before another part. You know, you want him to sort of hold together. But watch this. Okay? This is a Slinky, obviously. And if you didn't catch that, there it is in slow motion. Didn't expect that, did you? All right. I brought a Slinky, but you can almost see that I have the advantage of being on the top of the stage here. And I'll explain to you what's going on here. But that is unusual enough to me that it reminded me of what the Coyote was doing. So what's happening here is that you'll notice that the upper part of the Slinky is stretched more than the lower part of the Slinky. Why is that? Very good. You should consider a career in physics. So, at any rate, yes. This part of the Slinky has to hold up the whole Slinky, right? So there's more pulling on it than lower and lower and lower and lower. And in fact, why is right now the bottom part of the Slinky is pretty much stationary, right? Right before the fellow dropped it. The bottom part of the Slinky is where it is because even though gravity's pulling down on it, the rest of the Slinky is pulling up, right? And so when I let go of the top, here, I'll let go of the top, the rest of the Slinky is still holding the bottom. And it's not until the loops get close enough that the bottom of the Slinky knows that nothing is holding it up anymore that it starts to fall. So let's see if I can do in real life. Did that work? Yeah, pretty good. So I could show you this one more time. So this top part of the Slinky, the bottom part of the Slinky doesn't know that the top part of the Slinky is falling. Okay? It takes some time for that information to get there. And that's the picture. Anyway, so the Coyote stretching out like that is sort of like an inverted Slinky. But it is unusual to see what the Slinky does as well, and unexpected. At any rate, so part of what I conclude about cartoon physics is it's kind of realistic. Realistic enough that, that it entertains, and we don't get too hung up on the extremely bizarre things that happen here. Alrighty, so the last part of what we're going to talk about is about shooting a basketball. Okay, so I looked it up in the rule book. It says the objective of the game in the basketball is to put a 9.5-inch diameter ball through an 18-inch hoop that's mounted 10 feet above the floor on a backboard. Okay. And there are 5 players on a side. The rule book's full of things, but this is the challenge here, is to get this through there. Now, if you happen to be above the rim with a basketball in your hand, you can just drop it in, and that happens a lot in the game, of course. But getting there is half the fun, getting the ball above the rim like that. But let's just talk about actually shooting the ball. So, who actually has spent much time and joy shooting a basketball? More than that, really. That's it? Right? Okay. It takes a lot of practice, right? And maybe you can help me with some pointers here, but one of the obvious things is that because the ball is smaller by almost a factor of 2 in diameter than the rim is, that there is some margin of error. You can miss a little bit, and it still works. And the skill of shooting actually is to be good enough to be that accurate, to get it in the right place, but to also do things in the process of shooting that sometimes are called soft touch, etc., that increase the chance that if you do make a little bit of error, you'll still score the points. Right? So basketball, not very many of you raised your hands. But what do? What do they teach you in struggle? Which is, it has to do with the motion, right? And what about that motion? Okay, it's not like, I have a basketball here. All right, this is the way I learned it first. This is an interesting one. Right, so the very first foul shots I learned were like this, right? And we'll just call these Tim shots instead of all the other possible things. But at any rate, another thing about it was that it was important to actually give the ball a little bit of spin backwards, no matter how that happened. Is that something that they teach still when they're teaching basketball? Backspin is an important thing. And actually, as soon as things start rotating, physicists get excited. So we'll get to that. Okay, so this margin of error is a measure of how much you can miss by and still make the shot, still get the 2 points. So the margin of error, interestingly enough, depends on how the ball is coming down into the basket. The granny shot is what they really call it, tends to have a very high arc and come down onto the basket, not at 90 degrees, but fairly straight down. And it turns out that at 90 degrees, the margin of error, which is the distance between these two possible positions for the basketball, is about 8.5 inches. However, if it's coming straight down, the velocity you have to give it is effectively very large, or infinite, because it has to get from where you are forward at the same time. So you can't have exactly 90 degrees, but a little bit less than 90 degrees. And you have the largest possible margin of error. 60-degree shot is kind of unusual. That would be a very high arcing shot, and in which case the margin of error has been reduced to about 7, and the velocity with which you have to throw it is 9 meters per second. And 45 degrees is getting quite reasonable. In fact, it's quite optimal in many cases. And then the margin of error is much, much smaller, so you have to shoot much, much more accurately, but with significantly less velocity. So you can see the challenge here. If you want to make the basket effectively bigger, a larger margin of error, you have to throw the basketball harder. Throwing the basketball harder is hard to do accurately. And so you have to fine-tune a bigger number, 45 degrees. It turns out that this is empirical. This means that a scientist took a basketball team from Brooklyn College, apparently, and studied with very good shooters at what angle they were most successful, and found out that the angle was 45 degrees plus half the angle from the top of the player's hands to the rim. So if we draw a line from the player's hands to the rim, which is this line, and a horizontal line, which is this line, this is halfway in between, and I measure 45 degrees from there, and that is the angle that the ball should take. And this line isn't pointing directly to that because it's already arcing over there. Okay. So that is kind of the perfect shot, and there is the trajectory of the ball that has that. So this minimizes the effect of having the wrong initial velocity on the basketball. Here are some other possibilities here. If you have too shallow an angle, then the margin of error is much smaller. So it's harder to do. If you have a bigger angle, I showed you those before. Okay. So the other thing is the soft touch. I probably told you the answer already, but what is the key to the soft touch? Anybody? Yeah. Actually, not that one, if I saw you correctly. It's backspin. Right? It's backspin. So I have a somewhat detailed explanation of what backspin does. The shot there, I didn't actually expect that one, so let's look at that again. Okay, nice backspin on that. And that was Michael Jordan again. So here's a basketball. And we're going to think about the forces on that basketball as it is in flight. Okay? So a basketball in free flight, after it leaves the player's hands, what's the most obvious force on that basketball? Gravity, of course. Okay. So gravity, and that's downward. All right. And then the rest of the story I will tell you. This is moving through the air, and let's say it's moving up and to the right. Okay, so that's the direction of its velocity as I am considering it at this instant in time. And it's moving through the air. So the air is sort of like a wind that's pushing back on the basketball. And that causes drag, which slows the basketball down. That's important. The drag is opposite the velocity. So that's one thing. But in addition, we'll remove those for the sake of making our picture simpler. In addition, the player has put backspin on the basketball. And so that is backspin, right? The ball spinning this way as it moves forward. So we call that backspin. And the effect of backspin one of the effects is the basketball has little dimples in it. And those dimples produce some friction that drags air with the basketball as it's spinning. So there's a layer of air on the basketball that is spinning like this, and that's sometimes technically called a boundary layer. It's a layer between the sort of air out here and the basketball itself that travels with the basketball in more ways than one. But certainly it's spinning with the basketball. Okay? You understand? So now, let's just take a look at the top of the ball over here. The arrow, if you follow it around, is pointing to the left. Okay, so the velocity of the air in this part of the boundary layer is to the left, and the velocity of the air in this part of the boundary layer down here is to the right. Okay? This is in the same direction as the wind, and so that gives us a net effective speed of the wind at the top of the basketball. And this opposes the wind, so we have a shorter net wind speed at the bottom, a lower. So the air and the bottom of the basketball combining the wind and the boundary layer is lower velocity than at the top of the ball. So there's a difference in velocity of the wind, and this leads to lift. Just like an airfoil on an airplane wing, at some point you may have learned that the shape of the wing and the angle with which the wing goes through the air combine to make the air go over the top faster than the bottom of this. And an effect that's an airfoil effect, or Venturi is the name that's sometimes applied to this, is that there's more pressure on the bottom than the top, and that pushes up. And the basketball gets a little bit of lift from this. And so gravity is a bit counteracted by this spinning thing. So the spin gives lift to the ball, and that means that the ball does not have to be shot initially with as much velocity because it gets wind. So the ball has more hang time. This doesn't affect a player when they're doing hang time, but that changes the way that the ball moves. And so the ball is actually moving slower, which means it's less of a bad thing when the basketball doesn't quite hit its mark, is a little bit outside the margin of error. How far it bounces and everything else is significantly less because of this effect. There's another effect, which is the basketball is an object in air, so there's a little bit of buoyancy. That's on the order of 1%, but this effect can be tens of percent here compared to gravity, so that can really make a difference in the flight of the ball. So that's the reason, and the softening is really just slowing the velocity of the ball so that whatever it hits at a slower velocity and doesn't bounce as hard. So that's one thing about the spin. There's more, and that I show here. So here's a basketball on its way to the hoop, we think. It's spinning, okay? So it gets some lift, that's one thing, and so its trajectory follows this path, and then it's going to hit the backboard if you look at this path here. It's obviously going to hit the backboard, right? And if it hits the backboard, where will it go? Well, if we neglect the spin for a moment, you guys are smart, but nevertheless, if we neglect the spin for a moment This is the initial velocity, and it's basically a reflection. It's a fairly elastic collision. It bounces off in a way that this actually would be, without spin, the predicted trajectory. But as the basketball, with the dimples and everything, hits the backboard here, there's friction between the basketball and the backboard, and since the basketball is spinning this way, what direction is it pushing on the backboard? What direction is the basketball pushing on the backboard? Okay, it's pushing up in the direction of the arrow, and so the backboard pushes down. That's, by the way, major physics lesson, Newton's third law. The force of the ball on the board is up, and the force of the board on the ball is down, which means that instead of this trajectory, the ball follows that trajectory and goes through the hoop. And that was a three-point shot. Okay. So that's those are the points I wanted to bring up in this brief thing. I decided to kind of summarize everything with a bracket, just in case. You'll notice Michigan's not in this bracket anywhere, but sorry. So if we remember that in order to get a vertical jump of about 1 meter or 40 inches, it takes about 4 Gs of takeoff, no matter what the horizontal motion is. It takes about 9/10 of a second in the air and produces a meter of vertical, and often ends in a slam dunk. It's one of the reasons that it appears that the player is hanging in the air is that 71% of the trajectory is actually, 71% of the time is spent in the top half of the trajectory furthest from the ground. We also talked about margin of error, okay, which doesn't factor into hang time, but I needed to put it somewhere, okay. Cartoon physics is the result of a coyote. He still falls down, of course, as the Slinky did too, and that is one of the few of the things that we pointed out about cartoon physics. It would be interesting to look at a whole bunch of cartoons and figure out what's wrong with every one of them, but then it wouldn't be maybe as entertaining as it is. The best angle to shoot a basketball at with backspin is at 45 degrees plus the angle above the rim, and that is put together, makes the soft touch and a swish here. So this all put together is a pretty brief summary. I hope you enjoyed the movie and enjoyed this little discussion of the physics of Space Jam. And now, do you have any questions?
I was going to softball him one, but he already answered it during the lecture, so I'm at a loss. Any questions? Oh, let me come over there.
Do the women use a smaller basketball than the men?
Did you guys hear that? Do women use smaller basketballs than men?
I don't know. Actually, I don't know the women's game. They have the same size rim. I know that because they use the same court. But does anybody know? How much smaller? Possibly. Okay.
That would change the numbers around a little bit.
That's right. The margin of error would get bigger in every way. I guess there isn't very much dunking. There's a little bit, but not much dunking in that game. The backspin and the touch are extremely important. They're fabulous shooters, I know that. And the whole point of the spinning ball interacting with the backboard is the principle of the layup, of course.
Where's the center of mass on the falling Slinky?
Where is the center of mass on a falling Slinky? Oh, my Slinky's on the floor. The center of mass on a falling Slinky is moving because, at least if when it's stretched out, initially, because the lengths are all different distances apart. So, let's see. Thank you, Brian. Is this like a quiz for me? All righty. So let's see if we can kind of calculate where the center of mass is on this Slinky. It is pretty much, I might need some help with this. Guys in the front row. All right, so these are further apart. Okay, what we have to do is add up each link and the distance of the links until we get there. So when the links are closer together, there are more links, which means the center of mass is further down from the center. You guys agree with that? Yeah? Okay, and you already passed the qual and everything. So it's somewhere along here. All right, when I drop it, all right, it does not turn into a uniform mass Slinky right away. Okay, the parts that are in free fall are at first the top, and then as time goes on, more and more of this ends up in free fall. Okay. And so the center of mass obviously moves towards the center of the Slinky. When it gets down to here, the center of mass is clearly in the Slinky, and then it falls. Okay. So your next question is, or at least maybe your question was, is the center of mass of the Slinky falling with the acceleration of gravity? Okay. Because as the Slinky drops. What's the answer to that? Yeah, obviously. Well, maybe not obviously, but the answer is yes. So the center of mass, wherever it started, is now falling at exactly the same rate of anything that you drop. As soon as I drop it. Okay. Did that answer it? Okay.
We're seeing the Slinky shoot down because there's pressure, there's more force because the spring is extended at the top, right? That's why you're seeing that rush down?
Mm-hmm.
Okay, I was just wondering, maybe you spoke to that, but
I see. You mean that it's being pulled, actually?
Yeah, quicker because the spring is extended and there's more, is there more force? I'm not a physicist, but it seems like because the spring is elongated and it's under the tension of the plastic, it rushes to catch up because of that extra force on it before, I mean, I don't know.
So you're thinking that what it looks like is that the top is falling faster than gravity as it compresses, as the center of mass drops. The answer, I think, is correct. What you say is correct. And back to just what we said, is that the center of mass is falling just like a rock, okay? But the top is getting closer to the center of mass as time goes on. So it must be falling faster than a rock, which is correct. Good. Yeah.
I don't want to go back through your presentation, but I had a question about, you showed the different paths and flight paths.
Yeah.
You said that they're all, I think you said they were all the same amount of time.
No, I know what you're talking about. So, yes, that is correct. That is correct. That what matters is the height. So with the same vertical velocity. So there, of course, it's not entirely accurate that if you stand and jump, that you will get to the same height that you will if you're kind of running and jumping. But if you're running and jumping, you tend to also put some of the force and energy into the horizontal motion as well as the vertical motion. So this is a little bit of what I want to say, isolated or special case that I've drawn here, where the same height in everyone means that it's the same amount of time in the air. Yeah. Yeah, well, that is the nature, that is embodied in this right here, which is that the time and the distance only depend on the initial vertical velocity.
It seems like in the first case, you go higher to stay up as long as you would in the last case.
Yeah, but...
Then you go higher to stay up as long as the example on the right.
Yeah. We have... We actually, in the physics teaching facility, we have a very nice way of demonstrating this. And so it's going to be kind of a little bit hard to do, but I'm going to try it anyway. So what I'm going to do is from the same height, so we're only doing half of this. Instead of going up and down, we're just going to start at the top. Okay, this is about 1 meter. And I'm going to drop one ball, and I'm going to throw one ball forward. And I want you to tell me what the simple physics tells us is that these will spend the same amount of time falling, so they'll hit at the same time. Okay? So all I have to do to skillfully do this is to make sure that I impart only a horizontal velocity to this ball. Okay, so let's see if I can do it. Not quite, but pretty close. I'll try one more time. Machines are better than me, but the point of the discovery, if you will, was that the vertical velocity and the horizontal velocity are completely independent. Right? And so the time it takes to fall does not at all depend on how fast it's moving forward. So pretty close.
And if you put enough force to just throw it way up with your left,
Yeah.
I mean, it would stay up longer than the one you dropped. You're making the balance out the
Right. But okay, so I tried not to do anything tricky. All I did was,
I'm just saying, if you just threw it,
yeah.
as hard as you could out to your left, it
Okay.
would stay up longer than the one going straight down.
And no, it wouldn't. No.
You didn't put enough force into it to shock.
Well, in this case, yeah, I could throw it out. It would hit the wall and things like that. But no, really, it's actually the takeaway message here today is that all that matters is how far it falls. Yep. Yeah. Well, great. Yeah. I'm not sure where you can use that, but you just keep that in mind. So you'll see every one of these trajectories in the next basketball game. And one of the fascinating things is when you look at replays of anything these people do, every one of these launch and dunks are one of the amazing things where they run, maybe start at the foul line, even do a flip in the air. The center of mass still follows this trajectory, and then do the dunk. Every one of them takes less than a second. And then slow it down for you. You can watch the clock, and it does. At most you'll see it turn over 1 tick of a second. And if maybe that, watching those a few times will convince you that you've seen that. So this was the best I could do to kind of show it here, but it is in fact true that every one of these takes the same length of time for a 1 meter height, about 9/10 of a second. Yes?
From elementary school. Would a boulder kind of something time fall and then at the same time
If for any reason we could neglect some of the, like air resistance in particular, then they would, yes. And that's what Galileo did with 2 different size things. I have a chance to show you one more thing that has nothing to do, but I have the props here. Maybe I could have done it that way, right? Okay, so I have to get the bottoms at the same place. How am I doing? Is that about right? Okay. Right? So that's pretty, maybe not too surprising, but again, and if I did it from higher, etc. Okay. Yeah.
Any other questions?
I have a question.
Oh, our sound guy has a question.
Lance.
Lance.
I'm wondering when the coyote is falling, how his body falls first and his head stays level before his head falls the
Yeah.
coyote body.
Well, I'm leaving the realm of physics momentarily. But the reason is that the principle of cartoon, the main principle of cartoon physics, the whole field was founded on the principle that the coyote doesn't fall until he realizes that there's nothing holding him up. In fact, that's true for all of us, but we realize it right away. The coyote is a little slow. All right? And what part of the coyote is it that actually analyzes the situation in that? Well, it's the consciousness of the coyote, of course. And that's in his head. So until he's done with it, his head can't leave. But every now and then, the rest of him is subjected to physics eventually. And so that's why it starts off that way.
Thank you.
Yep.
All right, no more questions. Let's give him a big round of applause. Thanks for coming out. Science on Screen.